The universe holds a secret from its very first fraction of a second. That secret is written in the faintest tremors in the fabric of reality itself, ripples known as primordial gravitational waves. Finding them would be the ultimate breakthrough, a direct recording of the Big Bang and the violent cosmic inflation that followed. By the end of this exploration, you will understand 30 distinct and astonishing theories for what could have created these first space-time vibrations. We will confront ideas of colliding universes, cosmic strings thinner than an atom, and the possibility that our entire reality is a hologram. What single piece of evidence could force us to rewrite the story of creation? The quest for these first ripples begins with the most widely accepted origin story in modern cosmology. This is the theory of cosmic inflation, a cornerstone idea that has shaped our understanding of the universe's birth. According to this model, in the very first sliver of a second after the Big Bang, the universe did not just expand, it exploded outward at a speed far beyond that of light. Space itself inflated faster than light could cross it, stretching a region smaller than a proton to something larger than our entire observable universe in an almost incomprehensibly brief flash. This violent event did more than just create the vast cosmos we see. It also provided the perfect mechanism to create the primordial gravitational waves we are searching for today. The key lies in the quantum foam, the seething, turbulent energy that is thought to exist at the smallest possible scales. During inflation, the universe was dominated by a mysterious energy field called the inflation field. Like any quantum field, it was not perfectly smooth but was fizzing with tiny, random fluctuations in energy. These were mere microscopic tremors, insignificant blips on the quantum scale. But then inflation happened. That unimaginable stretching acted like a cosmic magnifying glass, taking those infinitesimal quantum jitters and blowing them up to astronomical proportions. The tiny wrinkles in the inflaton field were stretched into the seeds of all the galaxies and cosmic structures we see. And critically, the violent shaking of space-time itself during this expansion amplified those quantum tremors into literal waves in the fabric of reality, gravitational waves that have been traveling through the cosmos ever since. This theory makes a very specific and testable prediction. It says these ancient waves should have left a unique fingerprint on the oldest light in the universe, the cosmic microwave background radiation. As this primordial light traveled for over 13 billion years, passing through the ripples in space-time, its polarization, the direction its waves vibrate, would have been subtly twisted into a specific pattern known as B-mode polarization. Finding this faint, swirling pattern in the cosmic microwave background is the holy grail for experiments like BICEP at the South Pole and the upcoming Simons Observatory. It is a direct signal from the universe's first moment, a whisper from the era of inflation. Detecting it would not just confirm the existence of these space-time ripples, it would be a Nobel Prize-worthy validation of our entire cosmic origin story, proving that our universe truly was born in a storm of exponential expansion. But what if the universe's origin story is not a bang but a bounce? This is the core of the ekpyrotic scenario, a bold and beautiful alternative to cosmic inflation. Instead of a singular, explosive beginning from a point of infinite density, this theory proposes our universe is part of an eternal cycle of expansion and contraction. It suggests that before our Big Bang, there was a previous cosmic phase, a universe that was collapsing in on itself. This contraction reached a point of incredible density and energy, but not a true singularity. Then, like a cosmic spring, it rebounded. That rebound is our Big Bang, the moment our current expanding universe was born from the ashes of the old. This is the Big Bounce, a vision of a cyclical cosmos without a definitive beginning or end. To understand what could cause such a bounce, we must venture into the realm of string theory and its concept of extra dimensions. In this framework, our entire three-dimensional universe might be just one surface, a membrane or brain, floating in a higher dimensional space. The ekpyrotic model proposes that our Big Bang was not an explosion from a point, but the result of a collision. Picture two of these vast, flat brains, each holding its own universe, moving silently through a hidden dimension. They drift, they approach, and finally they collide. That titanic, multidimensional impact transfers an immense amount of energy into our brain, heating it to an unbelievable temperature and igniting the hot, expanding universe we observe. Our entire cosmic history, in this view, began with a crash. This fundamentally different origin story leads to a dramatically different prediction for the primordial gravitational waves we are searching for. In the inflationary model, the universe is stretched violently and exponentially, amplifying quantum fluctuations into powerful, long-wavelength space-time ripples. The ekpyrotic bounce, however, is a much smoother affair. The period of contraction before the bounce tends to iron out irregularities, smoothing the universe to an exceptional degree. When the bounce happens, it does not create the same kind of violent quantum shaking. Therefore, the theory predicts that the primordial gravitational waves from a bounce would be incredibly weak, perhaps even undetectably faint. Their frequency signature would also be distinct, lacking the specific pattern inflation imprints on the cosmic microwave background. This creates a clear cosmic litmus test. If experiments like the Simons Observatory detect the telltale swirling pattern of B-mode polarization in the ancient light, it would be a monumental victory for inflation. But if they search with ever-increasing sensitivity and find nothing, if the universe's first tremors remain stubbornly silent, that silence itself would speak volumes. It would be powerful, though indirect, evidence for a cyclical model, suggesting our universe was born not in a chaotic storm of inflation, but from a more ordered, graceful collision or rebound. The hunt for these first ripples is not just a search for a signal, it is a search for our true genesis, a way to distinguish between a universe born in a bang and one born from a bounce. The smooth predictions of inflation and the ekpyrotic bounce represent two ends of a spectrum, but the early universe may have been marked by far more violent and enduring scars. One of the most compelling and strange possibilities is that woven into the very fabric of our cosmos are relics called cosmic strings. These are not strings in any ordinary sense. They are theoretical flaws in the structure of reality itself, infinitely long filaments of pure energy thinner than a proton, yet so dense that a single inch of one could outweigh Mount Everest. They are thought to be topological defects, cracks that formed as the universe cooled and underwent dramatic phase transitions in its earliest, hottest moments. Much like cracks forming in ice as water freezes, these defects could have been permanently frozen into the expanding cosmos, creating a ghostly, indestructible web stretching across the entire universe. If such strings exist, they are not static. They would be under immense tension, whipping through space at nearly the speed of light in complex, oscillating loops. And every time a string snaps, crosses itself, or develops a sharp kink, it would create a cataclysm in the fabric of space-time. These events would not produce the smooth, background hum of gravitational waves predicted by inflation. Instead, they would generate sharp, cusp-like bursts of gravitational radiation, sudden and powerful tremors that would stand out starkly against the cosmic noise. Each burst would be a distinct non-Gaussian event in the data of our detectors, a spike, not a wave. Finding this signature would be like listening to a symphony and suddenly hearing a gunshot. It is a discrete, unmistakable signal of something catastrophic happening on a cosmic scale. The hunt for these tremors may not rely on the cosmic microwave background alone. Our best tool for catching the sharp snaps of cosmic strings could be a galactic-scale detector already in operation, pulsar-timing arrays. These projects use millisecond pulsars, the universe's most precise natural clocks, as a network of sensors. As the faint gravitational waves from a cosmic string event pass through our galaxy, they would ever so slightly speed up or slow down the arrival time of the pulsar's incredibly regular radio pulses. By monitoring dozens of these celestial metronomes across the sky for years, scientists hope to catch the telltale, correlated glitch that signals a passing ripple. A detection would be monumental. It would not only prove the existence of these bizarre one-dimensional relics, but would also provide a direct probe of physics at energies 1 trillion times higher than anything our particle colliders can reach, offering a frozen snapshot of the universe in its first terrifying moments of existence. The ghostly web of cosmic strings is not the only relic that could have filled the young universe with noise. Another profound possibility is that the cosmos was once a chaotic sea of tiny, ancient black holes. These are not the stellar mass giants born from dying stars or the supermassive behemoths at galactic centers. These are primordial black holes thought to have formed not from collapsed stars, but from the raw, churning density of the universe in its first second of existence. In that unimaginably hot and dense environment, random fluctuations in density could have been so extreme that pockets of space-time simply pinched off and collapsed under their own gravity, giving birth to black holes of almost any size. Some theories suggest the early universe could have been swarming with them, a vast population ranging in mass from a small asteroid to many times that of our Sun. This swarm would have been a gravitational maelstrom. These primordial black holes would have orbited each other, collided, and merged in a relentless, violent dance. And every single merger, every close encounter, would have sent powerful ripples through the fabric of space-time. The gravitational wave background from such a population would not be a smooth hum, but a cacophony, a dense chorus of overlapping chirps and rumbles from countless collisions happening across the cosmos. The frequency of these waves holds a critical clue. When two black holes merge, the frequency of the gravitational waves they emit is tied to their mass. Smaller black holes spiraling together faster produce higher-pitched ripples. Since many primordial black holes could be far lighter than those formed from stars, their merger signals would be in a much higher frequency range, far above what ground-based detectors like LIGO can hear. This shifts the hunt to a different frontier, space. Future missions like the proposed laser-interferometer space antenna, or LISA, are designed to listen for these higher-frequency cosmic whispers. By placing 3 spacecraft millions of miles apart in a precise triangle, LISA would create a gravitational wave observatory of astronomical scale, sensitive to the mergers of these ancient, lightweight black holes. Finding this specific signal would do more than reveal a new source of space-time ripples. It would solve one of the greatest mysteries in modern physics, the nature of dark matter. If a significant portion of that invisible, gravity-providing substance that holds galaxies together is actually made of these primordial black hole swarms, then their gravitational wave chorus would be the definitive proof. We would learn that the dark matter weaving through our galaxy is not an exotic particle, but the ancient, silent corpses of the universe's first and most violent moments. The violent chaos of a primordial black hole swarm offers one vision of the early cosmos, but there exists a possibility even more alien and grand in scale. Our universe may not be alone, and its first tremors could be the bruises from a cosmic fender bender with a neighbor. This is the multiverse-collision hypothesis, a theory that pushes the boundaries of cosmology into profoundly speculative territory. It builds upon the concept of eternal inflation, which suggests that the rapid expansion we think started our universe never truly stopped everywhere. Instead, in this view, our cosmos is just one bubble in a frothing, infinite sea of space-time. New bubble universes are constantly nucleating, like bubbles forming in a pot of boiling water, each with its own unique laws of physics, popping into existence within an eternally inflating background. Now imagine 2 of these expanding bubbles drifting in this higher dimensional foam. Their boundaries are walls of incredible energy. If they drift too close, they can touch. And when they do, the collision would be a cataclysm of almost unimaginable force, a shockwave of energy propagating through the newborn universe. For any observers inside one of those bubbles, that collision would be written into the very foundations of their reality. It would not create a uniform sea of gravitational waves like inflation might. Instead, the impact would be profoundly directional, coming from one specific region of the sky. The energy from the crash would imprint a distinct anisotropic pattern on both the cosmic microwave background and the background of primordial gravitational waves. It would be a cosmic scar, a directional whisper in the data. What would we look for? Theorists suggest such a collision could leave a telltale cold spot in the SIMB, a large, unexplained region of space that is slightly cooler than the surrounding glow. It might also create a specific, lopsided pattern in the polarization of that ancient light, or a distinct gradient in the strength of gravitational waves across the sky. Finding such a signature would be like discovering a massive dent in the hull of our universe, evidence that we are not an isolated creation but one bubble among countless others, bearing the marks of a long-ago encounter in the multiversal deep. It would mean the first ripples in our space-time were not the product of internal quantum jitters, but the echo of an external impact, the moment our reality literally bumped into another. The idea of colliding universes stretches our imagination to its limit, but an even more radical proposal suggests our reality may be an illusion of a grander sort. This is the holographic principle, a breathtaking concept born from the mathematics of black holes and string theory. It proposes that our seemingly three-dimensional universe with all its galaxies, stars, and planets is not fundamental. Instead, it is a projection, a cosmic hologram. All the information needed to describe everything within a volume of space, including you and me, is actually encoded on a two-dimensional surface that surrounds that volume, like the information on a security hologram is stored on a flat, shiny piece of foil. In this view, our rich three-dimensional experience is a magnificent and convincing illusion generated from data living on a distant, flat boundary. This is not science fiction, but a serious attempt by physicists to reconcile gravity with quantum mechanics. If this is true, then what are the primordial gravitational waves we are searching for? They cannot be simple ripples in a three-dimensional fabric, because that fabric is not the deepest layer of reality. In the holographic framework, these ancient tremors might be understood as something far more fundamental. They could be vibrations or even quantum error corrections on that ultimate two-dimensional screen where the universe's information is stored. Think of it like a glitch or a pixelation on the surface of the cosmic projector, a disturbance in the code that manifests for us as a ripple moving through space and time. This profound shift in perspective could dramatically alter our predictions for what the gravitational wave background should look like. The spectrum of these waves, their distribution across different frequencies, might carry a specific signature that reflects the quantum nature of the holographic screen itself. It could reveal a direct link between gravity, the force that shapes the cosmos, and quantum information theory, the rules governing data and computation. A detection of primordial waves with a specific pattern could, in theory, be analyzed to see if it matches the kind of signal expected from a quantum system on a boundary, offering a potential, though extraordinarily subtle, test for one of the most mind-bending ideas in all of physics. It suggests that by listening to the universe's first whispers, we might not just be hearing the birth of space, but reading the first lines of code from which space itself is rendered. The holographic principle redefines the very stage of reality, but the actors on that stage could be equally strange. Among the most elegant and sought-after characters in this cosmic drama are particles that have never been seen, actions. These hypothetical entities were first dreamed up not for cosmology, but to solve a deep and frustrating puzzle in the quantum world known as the strong CP problem. In simple terms, the equations of the strong nuclear force which glues protons and neutrons together seem to allow for a certain kind of asymmetry that would make particles like neutrons behave differently from their antimatter counterparts. Yet in our universe, no such difference is observed. The symmetry is perfectly preserved, as if a cosmic rule is being enforced with inexplicable precision. Actions were proposed as the universe's perfect enforcers, a new field that naturally sweeps this problematic asymmetry under the rug, restoring balance to the quantum realm. But if actions exist, their influence would have stretched far beyond the tiny world of quarks. In the seething energy of the early universe, the action field would not have been static. As the cosmos expanded and cooled after inflation, this field would have begun to oscillate, sloshing back and forth like a vast, invisible cosmic pendulum. These oscillations are not just a curious side effect, they are a potential powerhouse for gravitational waves. The mechanism at play is called parametric resonance. Think of a child on a swing. If you push the swing at just the right moment in its natural rhythm, each small push adds energy and the swing goes higher and higher. The oscillating action field can act in a similar way on the fabric of space-time itself. As the field rhythmically swings, it can transfer energy directly into any existing, faint ripples in space-time, amplifying them dramatically. In some models, it can even generate brand new gravitational waves from the quantum noise, like a cosmic loudspeaker turning a faint hiss into a clear, resonant tone. This process would not create a smooth background hum. Instead, it would produce a very distinct signature, a pronounced bump or peak in the gravitational wave spectrum at very specific frequencies. It is like looking at the audio spectrum of the universe's birth and seeing one note ring out far louder than all the others. This gives future detectors a precise target, a specific frequency range to scan with extra sensitivity. If we find that telltale peak, it would be a monumental double discovery. First, it would confirm the existence of primordial gravitational waves. Second, and perhaps more astonishingly, it would provide direct evidence for the action itself, solving a 40-year-old particle physics mystery and revealing that one of the universe's most fundamental symmetries is guarded by a ghostly, oscillating field that also orchestrated the first tremors of space and time. Actions offer an elegant solution to a quantum puzzle, but they still operate within the familiar framework of gravity as described by Einstein. Yet, what if the framework itself is wrong? For over a century, general relativity has been our unshakable guide to understanding gravity, from orbiting planets to colliding black holes. But it is a theory of the very large, tested in the relatively tame gravity of the modern universe. In the unimaginable furnace of the first moments, where energies were quintillions of times higher than anything in particle colliders, the rules may have been different. This leads us to a radical family of ideas known as modified gravity theories, where Einstein's masterpiece is not the final word, but merely a very good approximation that breaks down under the most extreme conditions. These are not wild guesses, but mathematically rigorous attempts to solve cosmology's biggest headaches, like the mysteries of dark energy and dark matter, by tweaking the fundamental equations of gravity itself. One prominent example is F of R gravity. In Einstein's equations, there is a key term called the Ricci scalar, denoted by R. It is a measure of how much the geometry of space-time is curved by the matter and energy within it. In F of R gravity, this simple R is replaced by a function of R, hence the name. Think of it like upgrading a basic volume knob on a stereo to a sophisticated equalizer. Instead of gravity's strength being set by one simple dial, you now have a complex control that can adjust how space-time responds to energy differently depending on the situation, especially in environments of incredible density or curvature. This subtle change in the mathematics has profound consequences for the birth of gravitational waves. In the standard inflationary picture under general relativity, the quantum fluctuations that get stretched into gravitational waves and the seeds of galaxies have a specific predicted relationship. It is a cosmic balance sheet. The theory predicts the relative strength or power of the tensor waves compared to the scalar density fluctuations. This ratio is a holy number for cosmologists. Modified gravity theories like F of R can directly alter this balance. They change how gravitational waves propagate through the seething early universe, potentially amplifying them or damping them down relative to the density ripples. The function F of R acts like a filter, selectively changing how the fabric of space-time itself vibrates. This means the primordial gravitational wave background we hope to detect could carry a direct signature of gravity's modified nature. If we can precisely measure the strength of these ancient ripples and compare it to the map of galaxy seeds imprinted in the cosmic microwave background, we are conducting a fundamental test. A mismatch from the prediction of standard general relativity would be a seismic event in physics. It would tell us that Einstein's theory, for all its glory, is incomplete. We would have evidence that gravity itself had a different character during the universe's violent birth, a character preserved like a fossil in the first tremors of space and time. The hunt is not just for waves, but for the true law that wrote them into existence. The search for a single note in the cosmic symphony may be too simple. Inflation's main actor, the inflaton field, might not have performed alone. A more nuanced and crowded stage emerges with the spectator field mechanism. In this variant of inflation, the universe's explosive expansion is still driven by the primary inflaton field, but it shares the early cosmos with other quantum fields. One of these is designated a spectator. It earns this name because it does not power the expansion. It simply rides along, a passive observer to the inflaton's dramatic work. But in the quantum realm, passivity is an illusion. Like every field, the spectator field was fizzing with its own inherent quantum fluctuations, tiny random variations in its energy. During inflation, while the inflaton's fluctuations were being stretched into the seeds of galaxies, the spectator's fluctuations were also being magnified and frozen into the fabric of the universe. They were imprinted but dormant. The real drama begins when inflation ends, as the inflaton field decays, reheating the universe into a hot soup of particles. The spectator field may also reach a critical point. It could become unstable and suddenly decay, or it could oscillate and transfer its pent-up energy into other forms. This decay is not a quiet affair. It is a violent release, a secondary explosion happening within the newborn hot universe. And crucially, this energetic decay can be an incredibly efficient generator of gravitational waves. The process is turbulent, like the churning of a pot of water brought to a rapid boil, creating waves on the surface. The collapse and transformation of the spectator field's energy create powerful ripples in space-time. The resulting gravitational wave signal could be far richer and more varied than the smooth background predicted by simple inflation. Because the spectator field's properties, its mass, its coupling to other particles, could be almost anything, its decay can produce a spectrum of waves with distinct features. It might create a pronounced bump at a specific frequency, a sudden rise and fall in the gravitational wave background that stands out like a mountain range on a flat plane. This signature is a direct fossil of the spectator field's unique character. Detecting such a feature would be like finding a specific instrument's melody within the orchestra's overall sound. It would tell us that the early universe contained more than just the inflaton. It would reveal the presence and properties of another fundamental field, a hidden actor that left its mark only in the tremors it created as it vanished. The gravitational wave background, therefore, becomes more than a confirmation of inflation. It transforms into a cosmic particle detector, its intricate shape potentially revealing the entire cast of characters that populated the universe in its very first moments. String theory offers a vision of the beginning that turns our intuition completely upside down. This is the pre-Big Bang scenario, a radical alternative where the universe did not emerge from a hot, dense singularity. Instead, it was born from a state of almost ghostly calm. Imagine a cosmos that is cold, nearly empty, and incredibly vast, but one where space itself is wound up with a different kind of tension. In this model, the universe starts in a state of very low curvature, meaning space is almost flat and uneventful, but it is filled with a different fundamental ingredient, a field called the dilaton. The dilaton is intimately tied to the strength of gravity itself. In this initial cold state, the dilaton field is very strong, making gravitational effects potent. Then something triggers a transformation. The dilaton field begins to evolve, and as it does, it drives a period of violent, accelerated expansion. But with a crucial twist, this expansion happens before what we call the Big Bang. The universe swells from a cold, dilute state into a hot, dense, and highly curved one. That moment of maximum density and temperature is our Big Bang. It is not the start, but the turning point, the climax of this pre-bang phase. What follows is the universe we know, expanding and cooling from that hot, dense state. This narrative relies on a beautiful and profound symmetry in string theory known as duality. Duality is a mathematical relationship that links two seemingly different descriptions of physics and shows they are actually the same reality seen from different angles. In the pre-Big Bang scenario, a specific duality connects the universe before the bang to the universe after it. The cold, dilute pre-bang era is mathematically mirrored or dual to the hot, dense post-bang era. They are two sides of the same cosmic coin. This elegant symmetry is not just philosophical, it leaves a distinct, testable imprint on the universe's first gravitational waves. Because the expansion dynamics before the bang are so different from standard inflation, the spectrum of primordial ripples it produces is flipped. Most inflationary models predict a red tilt for gravitational waves, meaning the longest wavelength waves are the strongest, with power decreasing as you listen to higher frequencies. The pre-Big Bang scenario does the opposite. It predicts a blue tilt. The power of these space-time ripples would actually increase as you move to higher and higher frequencies. It would be a rising chorus, growing louder in the registers our future space-based detectors are designed to hear. Finding this blue tilted spectrum would be more than just another data point. It would be a smoking gun for string-based cosmology. That rising whisper would be direct evidence that our universe underwent this mysterious, dualistic phase, that the Big Bang was a transformative bridge between two mirrored epochs of cosmic history. It would force us to accept that our universe's story began not with a fireball, but in a deep, cold silence waiting to ring. Symmetry is the silent architect of our universe's laws, but what if gravity itself harbors a secret preference for left over right? This leads us to the profoundly strange realm of Chern-Simons gravity, a theoretical modification where the force that shapes the cosmos becomes chiral-handed. In our standard picture, a gravitational wave is a ripple that stretches space in one direction while squeezing it in the perpendicular direction, and it does so impartially. A left-handed circularly polarized wave and its right-handed mirror image travel through the cosmos in exactly the same way, obeying perfect symmetry. Chern-Simons gravity introduces a subtle, parity-violating term into Einstein's equations that breaks this mirror symmetry. The concept often arises when we consider the universe not as empty space, but as a stage filled with particles that themselves have a handedness like chiral fermions. The ghostly sea of neutrinos, for instance, all spin in a way that relates to their direction of motion, like a left-handed screw. The interaction of gravity with this chiral cosmic background, or from specific structures in string theory, can effectively twist the fabric of space-time itself, making it act like a cosmic crystal for gravitational waves. The consequence is not subtle. In such a universe, left-handed and right-handed gravitational waves would no longer be equals. They would propagate at different speeds. One-handedness might travel slightly faster or be amplified while the other is dampened. Imagine sending two identical spirals, one clockwise and one counterclockwise, through a strange medium that slows one spiral down. They would arrive at different times, their symmetry broken. If this effect was active during the universe's violent birth, it would have imprinted itself permanently on the primordial gravitational wave background. The sea of ancient ripples would not be an even mix of left and right-handed waves. It would show a net circular polarization, a preference for one spinning direction over the other across the entire sky. This would be a signature of staggering importance. Detecting a circularly polarized gravitational wave background would be a direct observation of parity violation in gravity itself. It would mean that at the most fundamental level, the universe distinguishes between left and right through the force that binds it together. Such a discovery would force a rewrite of textbooks, revealing that one of nature's most cherished symmetries is broken in the gravitational sector, pointing unequivocally to new physics woven into the geometry of reality from the very first instant. The possibility of a chiral universe is breathtaking, yet it still assumes inflation unfolded in a vacuum, a pure quantum event. But what if the early cosmos was not cold and empty during this expansion, but was instead a seething, hot plasma from the very start? This is the core idea of warm inflation, a fascinating twist on the classic tale. In the standard cold inflation model, the inflaton field is largely isolated, a solo actor driving expansion in a universe that has been supercooled and emptied of all other particles. Its quantum fluctuations are the only game in town, stretched into the seeds of everything. Warm inflation paints a very different and perhaps more realistic picture. Here, the inflaton field is not alone. It is strongly coupled to a thermal bath of other particles, quarks, gluons, photons, all fizzing in a dense, hot soup. The universe during inflation is not cold and empty, it is a roaring furnace. This constant, intense interaction changes everything about how fluctuations are born. In this hot environment, the dominant seeds for cosmic structure are not the delicate, random jitters of quantum uncertainty. Instead, they are robust thermal fluctuations. Think of a pot of water just before it boils. You see tiny bubbles forming and popping chaotically, not from some quantum process, but from the sheer, relentless energy of the heated water. In warm inflation, the inflaton field is constantly jostled and bumped by the energetic particles in the thermal bath. These thermal kicks, these classical bumps and wiggles, are what get stretched by the expansion to become the galaxies we see today. The gravitational wave story changes dramatically because of this. In cold inflation, the quantum fluctuations of space-time itself get amplified into gravitational waves. But in the warm model, those space-time ripples are also drowned out by the classical thermal noise. The thermal fluctuations that seed galaxies do not efficiently produce gravitational waves in the same way. Consequently, warm inflation typically predicts a primordial gravitational wave signal with a much smaller amplitude, a far fainter whisper than its cold counterpart. This is not a minor detail, it is a potential solution to a growing cosmic puzzle. Our most sensitive experiments have yet to detect the telltale B-mode polarization from inflation. Could the reason be that we have been listening for the wrong kind of signal, expecting a quantum shout from a cold void when the true sound was a classical murmur from a hot and crowded early universe? If future observations continue to find only profound silence where we expected a raw, warm inflation offers a compelling explanation. It suggests the universe's structure arose not from ghostly quantum probabilities, but from the tangible, energetic churn of a primordial heat bath, a fundamentally more classical origin story written in the quiet of the first ripples. The universe's first tremors may have done more than just ripple through empty space. They could have been the cosmic dynamo that lit up the cosmos with its first magnetic fields, connecting two of astronomy's deepest mysteries. We see magnetic fields everywhere today, threading through galaxies, guiding star formation, and shaping the vast voids between clusters, but their origin is a profound puzzle. Magnets require moving electric charges, currents, to be born. In the early universe, before stars, before galaxies, where did those first currents come from? One elegant and powerful theory points directly to the primordial gravitational waves we have been discussing. The mechanism hinges on the primordial plasma, the seething, super-hot soup of charged particles, protons, electrons, and photons, that filled the universe after inflation. Gravitational waves are not just passive ripples. As they pass through a medium, they actively squeeze and stretch space itself. Now envision a powerful gravitational wave, one of those first tremors, moving through this charged plasma. As it passes, it rhythmically compresses and rarefies the soup of particles. This isn't a gentle motion. It is a violent shaking of the very arena in which these charged particles exist. That rhythmic compression can set the entire plasma into organized motion, creating waves of density and velocity within the sea of charged particles. And when you have a coordinated flow of charged particles, you have an electric current. According to this theory, these gravitational wave-induced currents could have been the seed, the initial spark that generated the universe's very first magnetic fields. It is a beautiful chain of causality. Quantum fluctuations stretched by inflation become gravitational waves, which then shake the primordial plasma to create currents, which finally generate magnetic fields that will be amplified over billions of years by the motion of gas within galaxies and clusters. This provides a stunning new way to hunt for those first ripples. If this theory is correct, then the magnetic fields we observe in the oldest, most pristine regions of the universe, in the faintest galaxies at the edge of time, should carry a specific signature. Their strength, their structure, even their alignment across the sky, could be a fossil imprint of the gravitational waves that birthed them. By using powerful radio telescopes to map these ancient magnetic fields in exquisite detail, astronomers might be able to work backwards, inferring the properties of the primordial gravitational waves that set them in motion billions of years ago. We would be reading the universe's magnetic memory to hear its first gravitational whisper, finding one hidden origin story written in the lines of force of another. The smooth continuum of space-time is the stage upon which all our physics plays out, but at the very smallest scales, this stage might dissolve into a kind of quantum foam. This leads to a radical reimagining of geometry itself, known as non-commutative geometry. In our everyday world and in all of classical and quantum physics, coordinates are simple numbers. You can specify a location with an x, a y, and a z value, and the order in which you list them does not matter. The point 5 meters north and 3 meters east is exactly the same as the point 3 meters east and 5 meters north. The coordinates commute, but in the extreme realm of the Planck scale, the fundamental graininess of reality may enforce a different rule. Here, space-time itself could become fuzzy. Its coordinates might cease to be simple numbers and instead behave more like the operators we find in quantum mechanics, where order suddenly matters profoundly. This is the essence of non-commutative geometry. A useful, though imperfect, analogy is to think of space-time at this scale not as a smooth sheet of graph paper, but as a material with a woven, textile-like structure. Trying to pinpoint an exact location becomes like trying to find a single, precise thread in a piece of cloth. You can get close, but there is an inherent fuzziness, a fundamental limit to how finely you can resolve a point. In this framework, the very concepts of here and there blur into a quantum uncertainty of position. This profound graininess of the cosmos would have directly shaped the birth of gravitational waves. In the standard inflationary picture, the quantum fluctuations that get stretched are vibrations of a smooth, classical space-time continuum. But if space-time was fundamentally fuzzy and non-commutative during that epoch, the rules for how those fluctuations are born and evolve change dramatically. The granular structure acts like a cosmic filter or a mesh screen. It can suppress the generation of the very shortest wavelength, highest frequency gravitational waves. Just as a fine mesh might block the tiniest particles of sand while letting gravel pass through, the non-commutative geometry of the early universe could have prevented the formation of gravitational ripples at the highest energies. This leads to a potentially observable signature, a sharp cut-off in the gravitational wave spectrum. Instead of the spectrum of ripples continuing to rise or fall smoothly across all frequencies, it would simply vanish above a certain high-frequency threshold, a direct imprint of the fundamental pixel size of reality. Furthermore, the strange correlations imposed by non-commuting coordinates could weave intricate, non-local patterns into the gravitational waves that do form. These patterns would be a unique fingerprint, a kind of quantum gravity barcode embedded in the ancient tremors. Detecting such a cut-off or these specific correlations would be nothing short of revolutionary. It would not merely confirm the existence of primordial gravitational waves. It would provide our first direct experimental evidence for the quantum nature of space and time themselves. We would move from theorizing about a foamy, granular structure to actually measuring its texture, reading the literal grain of the universe from the echoes of its birth. This granular structure of space-time hints at a deeper architecture, a hidden scaffolding that may define reality itself. Within the framework of string theory, our entire universe could be a three-dimensional island, a membrane, adrift in a higher dimensional sea. This vision gives rise to a spectacularly violent origin story for both inflation and its gravitational waves, known as the Big Splat. In this model, the driver of cosmic inflation is not an abstract field, but a physical object in motion. Picture our three-dimensional universe as one such membrane or brain, floating parallel to another in a higher dimensional space called the bulk. They are drawn together by a force, perhaps a kind of tension, like two vast sheets of cosmic fabric pulled toward one another. As they move through the bulk, the space between them shrinks, and the potential energy of their separation fuels a period of exponential expansion within each brain. This is brain inflation, a period of rapid growth powered not by a field's energy, but by the kinetic energy of impending collision. The climax of this story is not a graceful merger, but a cataclysm. When the brains finally meet, they do not pass through each other softly, they collide. This is the Big Splat, a multidimensional impact of unimaginable force. For any observer living on one of those brains, this event would be the definitive end of inflation and the beginning of the hot, dense universe we recognize as the Big Bang. The collision would be a cosmic thunderclap, a release of pent-up energy so immense it would reheat the entire brain into a seething plasma. And crucially, this splat would not be silent. The violent, sudden stopping of the brain's motion would send a titanic shockwave rippling through the very fabric of space-time. This shockwave would manifest as an extraordinarily loud but transient burst of gravitational waves. Unlike the smooth, persistent hum predicted by many models, this signal would be a sharp, distinct chirp, a singular event echoing from the dawn of time. Its profile is key. The frequency of this burst is tied directly to the scale of the extra dimensions and the energy of the collision. Theorists calculate that for certain plausible sizes of the bulk space, the frequency of this primeval chirp could fall right into the sweet spot for future space-based observatories like the laser-interferometer space antenna. LISA design, with its million-kilometer arms, is perfect for catching these mid-frequency ripples. Finding such a signal would be a discovery of unparalleled significance. It would be a direct recording of the Big Splat itself. More than that, the precise shape of the chirp, its duration, its frequency evolution would act as a cosmic sonogram. By analyzing it, scientists could deduce the dimensionality of the bulk space, the tension of the brains, and the energy of the impact. we would move from speculation to measurement, confirming not only the existence of extra dimensions, but also revealing the specific, violent mechanics that ignited our universe. The first tremors of space-time could literally be the sound of our world colliding with another in a hidden, higher realm. The collision of brains offers a violent ignition, but the universe's expansion may have been steered by a force that never left. Dark energy is the dominant actor in our cosmic present, a mysterious pressure causing the expansion of space to accelerate. Yet its nature remains one of physics' greatest enigmas. What if this enigmatic force was not a constant, passive presence, but had a wild, dynamic youth? This is the theory of early dark energy, which proposes that the substance driving our universe's acceleration today was far more potent and active in the first moments after the Big Bang. In this scenario, dark energy was not a late-arriving guest to the cosmic party. It was there from the very beginning, playing a crucial role in shaping the infant universe. It would have been a powerful, evolving field that interacted with the star of the show, the inflaton field that drove inflation. Their relationship would have been a complex cosmic dance. As the inflaton field rolled down its energy hill, driving the explosive expansion, the early dark energy field could have been oscillating or evolving alongside it. Their interaction would not have been a silent coexistence. The energy and pressure of this early dark energy would have exerted a direct influence on the rate of the universe's expansion during those critical moments. Since the production of gravitational waves is exquisitely sensitive to the expansion rate, how fast space is being stretched, any modulation from a companion field would leave a permanent mark. The result would not be a smooth, featureless spectrum of gravitational waves. Instead, the interference between the inflaton and this early dark energy could have imprinted oscillatory features, wiggles, or distinct steps onto the power spectrum of the primordial ripples. It would be like listening to a steady tone that suddenly develops a warble or a rhythmic pulse, a clear sign of a second instrument playing in the cosmic orchestra. Finding such features in the gravitational wave background would be a discovery of profound interconnectedness. It would directly link the universe's explosive birth to its long-term destiny. We would learn that the same fundamental ingredient that is now gently pushing galaxies apart was once a vigorous participant in creation itself, its early activity fossilized in the tremors of space-time. This theory transforms dark energy from a modern puzzle into an ancient architect, suggesting that the force determining the universe's ultimate fate was also a key sculptor of its first structures. The early universe was a place of unimaginable heat and unity, where the forces we know as separate today were once fused into a single, perfect symmetry. Then, as the cosmos expanded and cooled, it underwent profound changes of state, cosmic phase transitions that fundamentally reshaped reality. These were not gentle shifts, but dramatic reorganizations of the vacuum itself, and they may have shaken the fabric of space-time with incredible violence. The most pivotal of these was the electroweak symmetry breaking. In the first trillionth of a second, the electromagnetic force and the weak nuclear force were one and the same, a unified electroweak force. As the temperature plummeted, this perfect symmetry was broken. The Higgs field, which had been zero everywhere, suddenly acquired a non-zero value, like a vast ocean finding its new level. This event gave mass to particles like the W and Z bosons, splitting the single electroweak force into the two distinct forces we observe today. But how did this transition actually happen? The process could have been far more dramatic than a smooth, uniform shift. It may have been a first-order phase transition. Think of water freezing into ice. Under the right conditions, it doesn't freeze all at once. Instead, tiny bubbles of ice nucleate randomly throughout the liquid, then expand and merge until the entire volume is frozen. A first-order cosmic phase transition would have unfolded in a similar but exponentially more energetic way. In the seething early universe, pockets of the new, lower-energy vacuum, where the Higgs field had settled into its new state, would have spontaneously formed like bubbles in a boiling pot. These were not mere pockets of space, but domains of a new reality, bounded by walls of concentrated energy. Each bubble would then expand at nearly the speed of light, its walls sweeping through the surrounding high-energy vacuum and converting it. The cosmos would have been a chaotic froth of colliding vacuum domains, and when these expanding bubbles finally met, their walls would not just disappear quietly. They would collide, merge, and annihilate in bursts of phenomenal energy. This turbulent process of bubble nucleation, expansion, and collision would have been a gravitational wave powerhouse. The violent motions of the bubble walls, their collisions, and the resulting sound waves in the primordial plasma would have churned the fabric of space-time itself, generating a cacophony of ripples. This creates a gravitational wave background with a very specific character. Unlike the smooth hum from inflation, the signal from a first-order phase transition would have a pronounced peak at a particular frequency. That frequency is a direct echo of the energy scale of the transition itself. The size of the bubbles when they collided determines the characteristic wavelength of the waves they produced. A transition that happened earlier at a higher energy would produce bubbles that collided when the universe was smaller, leading to gravitational waves that today have a higher frequency. This gives us a remarkable tuning fork for the cosmos. If we can detect this primordial gravitational wave background and identify a distinct peak in its spectrum, we can read the frequency like a cosmic thermometer. It would tell us the precise temperature and thus the energy at which this universe-altering phase transition occurred. It would be a direct probe of physics at energies a quadrillion times beyond the reach of any particle collider, revealing not just that the forces split, but exactly how violently that divorce took place. The faintest tremors in space could carry the precise signature of the moment our universe cooled into the differentiated reality we call home. The universe's contraction could be a creative force, not merely an ending. This brings us to the matter bounce, a second profound vision of a cyclical cosmos that offers a radically different path to our reality. In this model, the universe does not bounce from a collision of brains or a mysterious stringy state. Instead, it contracts under the familiar classical reign of matter and gravity. Picture a cosmos that has already lived a long life, expanding and evolving until its gravitational pull finally overcomes its outward momentum. It begins to collapse not in a fiery plasma, but in a phase dominated by cold, non-relativistic matter, dust and dark matter slowly gathering under their own weight. As space shrinks, everything is drawn together. Galaxies would appear to rush toward each other, the background temperature of space would rise, and the night sky would grow brighter. Yet within this grand classical contraction lies a subtle quantum secret. The universe is never perfectly smooth. Even in this collapsing phase, tiny quantum fluctuations in the matter field exist, microscopic ripples in density. And here is the beautiful twist. In the contracting phase of a matter bounce, these quantum fluctuations do not get ironed out. They get amplified. As space shrinks, it squeezes these tiny seeds, stretching their wavelengths and increasing their amplitude. The contraction itself acts as the engine that magnifies quantum noise into cosmic structure. By the time the universe reaches its moment of maximum density and bounces into a new expansion, those amplified fluctuations are already imprinted as the ready-made seeds for galaxies, clusters, and the entire cosmic web we see today. They also become the source for primordial gravitational waves, as the shaking of matter during contraction vibrates the fabric of space-time. This leads to a key, testable prediction that echoes one from the depths of string theory. The gravitational waves generated in a matter-dominated contraction would exhibit a strong blue tilt. Their power would increase dramatically at higher frequencies, creating a rising chorus in the spectrum. This is not because of quantum gravity effects, but a direct consequence of classical general relativity governing a universe filled with matter as it collapses. The dynamics of that contraction naturally favor the production of shorter wavelength ripples. Detecting such a blue-tilted spectrum would therefore present a fascinating puzzle. It would match a prediction from the string-theoretic pre-Big Bang scenario, yet it would arise from a completely different, non-inflationary mechanism rooted in Einstein's own equations. Even more strikingly, the matter bounce naturally produces a flat universe, one of the great successes of inflation, simply through the smoothing effects of the long contraction phase. A single observation could therefore force us to choose between two vastly different stories, one of quantum strings in a pre-Bang epoch, and another of a grand, classical collapse of a previous universe made of stuff we already understand. The first ripples might not speak of a beginning, but of a majestic, eternal return. Supersymmetry offers a vision of the early cosmos where every particle had a hidden twin. This elegant theory, often called SUSY, proposes a deep and fundamental symmetry between the two great families of particles that make up reality: fermions like quarks and electrons, which are the building blocks of matter, and bosons like photons and gluons, which carry the forces between them. In a supersymmetric universe, for every known fermion, there should be a bosonic superpartner, and for every known boson, a fermionic one. The electron would be paired with a selectron, the photon with a photino, the quark with a squark. This doubling of the cosmic cast list is not just mathematical beauty. It is a potential solution to some of the greatest puzzles in particle physics, like the staggering weakness of gravity compared to the other forces. But if supersymmetry is real, it would have left its most dramatic signature not in our colliders today, but in the furnace of the universe's first moments. The hot, dense plasma just after the Big Bang would have been teeming not just with standard particles, but with their superpartners as well. This changes everything about the energy budget of the infant cosmos. The equation of state, which describes how pressure relates to energy density in a fluid, would have been fundamentally altered. A universe filled with both particles and their superpartners has different thermodynamic properties than one with just the standard set. This shift in the cosmic equation of state would have directly influenced the dynamics of inflation and the violent period of reheating that followed. The inflatoned field, as it decayed to fill the universe with particles, would have interacted with this richer zoo of superpartners. These interactions could have made the transfer of energy more efficient or more turbulent, dramatically changing how the universe transitioned from a state of rapid expansion to a hot, dense soup. And where there is turbulent energy transfer, there are gravitational waves. The presence of supersymmetric particles could have turned the reheating phase into a far more powerful gravitational wave generator. The collisions and decays involving superpartners could have injected more energy into the vibrations of space-time, amplifying the primordial hum to a potentially detectable roar. Conversely, in some models, the new particles could have dampened certain processes, leading to a quieter signal. The key point is that the spectrum of primordial gravitational waves we hope to detect would carry a measurable imprint of supersymmetry's early role. The shape, amplitude, and even the frequency of that background ripple could reveal whether the early universe was supersymmetric. This means our most sensitive telescopes, pointed at the cosmic microwave background or listening with gravitational wave observatories, are not just cosmological instruments. They are the most powerful particle colliders we will ever build, probing energies 1 trillion times beyond the reach of the Large Hadron Collider. The hunt for the universe's first tremors has become a hunt for the ghostly twins of every particle we know. The smoothness of the universe might have been guaranteed by a fundamental symmetry of nature itself. This is the anomaly-induced inflation model, a theory that dispenses with the need for a special inflatoned field altogether. It proposes that the driving force behind the universe's explosive expansion was not a new particle or a mysterious energy, but a quantum quirk embedded in the very laws of physics. At the heart of this idea is conformal symmetry, a principle that suggests the laws of physics should look the same at all scales, from the subatomic to the cosmic. In a perfectly conformal world, there is no inherent ruler, no fundamental unit of length. Yet our universe clearly has scales: protons, people, planets. This symmetry is broken, and the mechanism of that breaking holds the key. During the universe's earliest, hottest phase, it may have been dominated by a large number of massless particles, a situation where conformal symmetry is nearly perfect. But quantum field theory introduces a subtle flaw into this perfect symmetry, known as a conformal anomaly. It is a mathematical inevitability, a tiny crack in the mirror of scale invariance that appears when quantum effects are taken into account. This anomaly generates a small but potent effective vacuum energy, and according to this model, that quantum-generated energy is what powered inflation. It is an elegant, economical idea. Inflation was not sparked by a new, ad hoc field, but was an inevitable consequence of the quantum behavior of the particles that were already there. The gravitational waves born from this process carry a distinct signature of their origin. Because the inflation mechanism is so different, the relationship between the tensor waves, the space-time ripples, and the scalar perturbations, the seeds for galaxies, is uniquely altered. In standard inflation, the energy scale of the event directly determines the strength of the gravitational waves, leading to a specific prediction for a parameter called the tensor-to-scalar ratio. In anomaly-induced inflation, this ratio is predicted to be exceptionally small, vanishingly faint. The model naturally produces a universe that is incredibly smooth and flat, with density perturbations to seed galaxies, but with a gravitational wave background so quiet it borders on silence. This presents a compelling answer to a growing observational puzzle. Our most sensitive telescopes, like the BICEP array at the South Pole, have been searching the cosmic microwave background for the swirling B-mode pattern, the telltale sign of primordial gravitational waves. So far, they have found nothing but profound quiet. While this is a challenge for many popular inflationary models that predicted a louder signal, it is exactly what the anomaly-induced model anticipates. The current non-detections are not a failure but a potential clue, pointing toward an inflation driven not by a dramatic new field, but by the quiet, inevitable mathematics of quantum anomalies. It suggests the universe's majestic smoothness was not an accident of a special field, but a fundamental rite of passage written into quantum law. The universe's first moments may have been a tangled web of vibrating threads. String gas cosmology offers a radically different vision of the beginning, one built not on fields or brains, but on the fundamental ingredients of string theory itself. In this model, the early cosmos was not a smooth, empty space undergoing inflation. It was a hot, dense, and chaotic gas of the most basic entities, tiny, vibrating loops and strands of energy, the fundamental strings. This stringy plasma existed in a remarkable state of balance known as the Hagedorn phase. Named after the physicist who studied the thermodynamics of such systems, this phase is a cosmic limbo. In it, the temperature of the universe is pinned near a maximum possible value, the Hagedorn temperature. Adding more energy to this seething gas does not make it hotter. Instead, it simply creates more strings. The universe in this state is quasi-static, hovering in a prolonged, nearly unchanging equilibrium, a simmering pot that refuses to boil over. This is the starting point, a universe of pure hot stringiness. The transition out of this phase is where the drama and the gravitational waves are born. As the universe finally begins to expand and cool, moving out of the Hagedorn phase, a crucial process unfolds. In a universe with three large spatial dimensions like our own, strings can exist in different states. Some are momentum modes, vibrating and moving freely. Others are winding modes, strings that are literally wrapped around the compact dimensions of space, like rubber bands stretched around a cylinder. In the hot, dense early universe, these winding and anti-winding modes are abundant, and they are in a sense trapped, preventing a rapid expansion. For the universe to grow, these winding modes must annihilate each other, and when they do, it is a cataclysmic event on a microscopic scale. The annihilation of these wound-up strings releases bursts of energy and creates violent perturbations in the background. This turbulent process of unwinding the cosmos acts as a potent generator of space-time ripples. The gravitational waves produced in this string gas scenario carry a signature that is becoming a familiar alternative theme, a strong blue tilt. The dynamics of the string interactions and annihilations naturally produce a spectrum where the power of the gravitational waves increases with frequency. This rising chorus is a direct prediction of the model, a clear and testable alternative to the red tilted spectrum predicted by most simple inflationary models. Once again, the shape of the gravitational wave background becomes a cosmic fingerprint. A detection of a blue tilted spectrum would force us to seriously consider that our universe began not as an empty void stretched by a field, but as a hot, tangled soup of the most basic building blocks of reality, shaking themselves free to create the space we now inhabit. Every force has a messenger, and for gravity, that particle is the graviton. This ghostly, massless particle has never been detected, but its existence is the logical conclusion of describing gravity within the quantum framework. Yet what if this messenger is not just a carrier of the force, but a hidden component of the cosmos itself? A highly speculative but fascinating theory suggests that the primordial gravitational wave background could actually constitute a form of dark matter, not through the waves themselves, but through the particles that make them up. In this vision, the universe is filled with an ocean of ultralight gravitons, the quantum units of the space-time ripples we have been discussing. They would be the leftover relics from the violent processes of the early universe, a permanent hum of quantum gravity frozen into the fabric of reality. For this to work, these gravitons must have a tiny, almost negligible mass. If they were completely massless like photons, they would travel at light speed and never clump together under gravity, making them useless for explaining the dark matter that holds galaxies together. But if they possess an infinitesimal mass, they would move slowly, and over cosmic time, they could coalesce under their own gravity into the vast, diffuse halos that surround galaxies. The challenge is one of incredible delicacy. The energy density of this gravitational wave dark matter must be exquisitely tuned. It must be substantial enough to account for roughly 85% of the matter in the universe, yet so diffuse and non-interactive that it has evaded every other form of detection for decades. The gravitational waves themselves would be of such low frequency and amplitude that they would form a near-uniform background, more like a still ocean than crashing waves. How could such a field be produced? One possibility lies in a specific kind of early universe production mechanism. Certain models of inflation or other primordial events could generate not chaotic waves, but a coherent, oscillating field of these ultralight particles. Think of it not as a random sea of ripples, but as a single, vast, rhythmically pulsing entity that fills all of space. This coherent field would behave like a perfect, frictionless fluid. It would not bump into atoms or scatter light, which is exactly why we cannot see it. It would simply be there, exerting a gentle gravitational pull on everything that passes through it, guiding the motion of stars within galaxies without ever making its presence known through a collision. The beauty of this idea is its unification. It proposes that the solution to two of cosmology's greatest mysteries, the nature of the universe's first tremors and the identity of dark matter, are one and the same. The whispers from the dawn of time are not just signals from a bygone era, they are the invisible skeleton of the cosmos today. While the evidence remains elusive and the theory faces immense hurdles, it reframes the entire quest. Finding the primordial gravitational wave background would not just be a look into the past. It might be the moment we finally put our hands on the dark, unseen substance that has shaped our cosmic present all along. A universe without a boundary, without a singular point of creation, is the astonishing vision of the no-boundary proposal. Conceived by physicists James Hartle and Stephen Hawking, this idea ventures beyond the classical Big Bang into the realm of quantum cosmology. It asks a question that reframes everything. What were the boundary conditions of the universe at the instant of its birth? In classical physics, the Big Bang is a singularity, a point where all known laws break down and our story hits a wall. Hartle and Hawking proposed there was no wall. They suggested the universe has no boundary in time, just as the surface of the Earth has no edge. To make this work mathematically, they employed a brilliant trick, a rotation into what is called imaginary time. This is not time as we experience it, but a mathematical device that turns the problem of the universe's beginning into a problem of geometry. In this picture, the four-dimensional history of the cosmos is likened to the surface of a sphere. The Big Bang is not a point on that surface, but rather the South Pole. If you stand at the South Pole, there is no boundary, no edge, no before. You simply are at a location where all lines of longitude meet. The universe in this view is finite in extent but has no singular starting moment. It is a smooth, closed surface without a boundary. This geometry is not a certainty but a probability. Hartle and Hawking derived a wave function for the entire universe, a mathematical expression that assigns probabilities to different possible initial geometries and configurations. The most probable universe, according to this wave function, is one that is exceptionally smooth, flat, and large from the outset. It is a universe that emerges from the quantum fog already looking remarkably like the one we observe, without the need for a prolonged period of inflation to iron out wrinkles, though inflation can still occur within this framework as a subsequent event. This foundational smoothness has a direct and profound implication for the primordial gravitational wave background. A universe born in the most probable no-boundary state is inherently quiet. The quantum fluctuations that get stretched into gravitational waves are themselves suppressed in this smooth beginning. Therefore, the no-boundary proposal naturally favors inflationary models that produce a very low amplitude of gravitational waves, a faint whisper rather than a definitive shout. It predicts a tensor-to-scalar ratio that is extremely small, potentially at the very limit of or even beyond our ability to detect. In a sense, the profound silence our most sensitive experiments have so far encountered is not a puzzle for this model, but an expected feature. The hunt for those first ripples becomes a test of cosmic initial conditions themselves. A loud, clear detection would challenge the no-boundary idea, suggesting a more chaotic or structured beginning. But if the silence persists, if we find only an ever deeper quiet, it would lend powerful support to the vision of a universe that simply appeared, smooth and complete, from a state with no boundary, no edge, and no singular moment of creation at all. The smooth geometry of a no-boundary universe is a profound vision, but our reality may be folded into shapes we cannot directly perceive. The fabric of space-time we experience has three spatial dimensions, yet many of our most promising theories of quantum gravity demand more. They propose that our universe is embedded within a higher dimensional arena, and this hidden architecture would have directly sculpted the universe's first gravitational ripples. Consider the Randall-Sundrum model, a compelling framework where our entire three-dimensional cosmos is a membrane or brain floating within a five-dimensional bulk. In this picture, gravity is fundamentally a force of the higher dimensional space, while the other forces are trapped on our brain. This single change to the cosmic rulebook has dramatic consequences for gravitational waves. When a ripple in space-time forms on our brain, perhaps from an ancient cosmic event, it does not have to stay confined here. Like a sound wave traveling from a single room into a vast, open hall, the gravitational wave can leak. It can propagate off our brain and into the infinite expanse of the bulk dimension. For us, confined to our three-dimensional slice of reality, this leakage would make the wave appear weaker, its signal diluted as its energy dissipates into the unseen dimensions. Our detectors would measure an amplitude that seems too faint, a whisper that hints at a greater volume of space we cannot access. This provides a potential solution to a puzzling observation. If we one day detect the primordial gravitational wave background and find it to be surprisingly quiet, weaker than our models of inflation predict, it may not mean our models are wrong. That silence could be the key signature of extra dimensions, the sound of the universe's first tremors echoing into a hidden realm, but leakage is only one clue. The very nature of the waves themselves would be transformed. In Einstein's four-dimensional universe, a gravitational wave has only two allowed polarization states, plus and cross, patterns that stretch and squeeze space in perpendicular directions. These are the only vibrations a four-dimensional fabric can sustain. Introduce a fifth dimension, however, and new vibrational modes become possible. The fabric can now ripple in ways that are strictly forbidden in standard general relativity. One of the most telling would be the breathing mode. Imagine space itself rhythmically expanding and contracting in all directions simultaneously, like a cosmic lung inhaling and exhaling. This scalar polarization is impossible in a pure four-dimensional world, but it becomes a natural vibration in a higher dimensional geometry. Detecting this extra polarization state in the primordial gravitational wave background would be a discovery of almost unimaginable impact. It would be direct, incontrovertible evidence that our universe has more than three spatial dimensions. The first tremors of creation would carry within their very pattern the blueprint of reality's true shape, revealing that we live on a membrane within a grander, hidden architecture. Every ripple would be a message from the bulk, a literal higher dimensional vibration imprinted at the dawn of time. Our journey through the cosmos has taken us to the edge of known physics, but a deeper mystery lurks within the very equations of inflation. This is the trans-Planckian problem, a profound conceptual challenge that forces us to question the limits of our own theory. To understand it, we must rewind the cosmic film with extreme precision. We see a particular ripple in space-time today, a gravitational wave with a wavelength of, say, a light year. We trace its origin back through 13.8 billion years of expansion, all the way to the moment of its birth during inflation. As we rewind, the universe shrinks and the wavelength of that ripple shrinks with it. When we reach the moment it was created, we find something astonishing. According to our standard calculations, that ripple, which today stretches across trillions of miles, originated with a wavelength far, far smaller than the Planck length. This is the fundamental scale of quantum gravity, a distance so tiny it is about 20 orders of magnitude smaller than a proton. It is the realm where space and time themselves are thought to dissolve into a foamy, chaotic quantum geometry. Our trusted theory of inflation confidently tells us the story of this ripple's life, but it begins that story in a place where the theory has absolutely no right to speak. It is as if a biographer wrote a detailed account of someone's entire life, starting from the precise moment of their conception, but using the laws of biology that govern adult humans. The physics of the Planck scale is unknown territory, governed by a theory of quantum gravity we do not yet possess. So how can we trust any prediction that depends so critically on that first instant? This is the trans-Planckian problem in its starkest form. It suggests our beautiful inflationary narrative might be built on a foundation of sand, extrapolating known physics into a domain where it almost certainly breaks down. Yet, rather than a fatal flaw, this problem presents a breathtaking opportunity. If new physics does govern the Planck scale, it would have left its mark on those infant ripples as they were born. The unknown quantum gravity of the first moment would have imprinted a signature on the gravitational waves as they crossed the threshold from the trans-Planckian realm into the domain where our classical physics takes over. What might that signature look like? Theorists working with frameworks like string theory or loop quantum gravity suggest several tantalizing possibilities. One is a series of oscillations, fine wiggles superimposed on the smooth gravitational wave power spectrum. These would be like interference patterns, echoes from the moment the ripple's wavelength stretched beyond the fundamental grain of space-time. Another possibility is a sharp cutoff. Just as a mesh screen blocks particles smaller than its holes, the granular structure of space at the Planck scale could have prevented the creation of gravitational waves with frequencies higher than a certain threshold. The spectrum would simply terminate, a sudden silence marking the pixelated edge of reality. There could even be specific correlations or non-Gaussian features, subtle statistical fingerprints of the quantum gravitational process that gave birth to the waves. Hunting for these features is not merely an exercise in cosmology. It is a direct hunt for the fingerprints of quantum gravity itself. Our most powerful particle colliders on Earth probe energies 1 trillion times too weak to access the Planck scale. But the universe, in its first moments, was a natural accelerator of inconceivable power. The primordial gravitational waves are messengers from that epoch, and their detailed structure is a data stream from the quantum gravity regime. By analyzing the shape of the gravitational wave background with exquisite precision, we are attempting to read a message from a domain where space and time are no longer smooth and continuous but quantized and wild. A detection of trans-Planckian signatures would be a landmark in human understanding. It would validate the incredible power of cosmology as a fundamental physics laboratory and provide our first experimental clues to a theory that unifies gravity with the quantum world. The faintest tremors from the beginning could carry the first hard evidence of the true, granular nature of reality. A hidden field could be actively disguising itself from our detectors. This is the core of the chameleon field, a hypothetical scalar particle with a truly bizarre property. Its mass is not fixed. Instead, it changes dramatically based on its surroundings, like a cosmic chameleon changing its color to blend in. In regions of high density, like within a planet or a star, the chameleon field becomes incredibly massive and short-ranged, effectively hiding itself from view. This screening mechanism explains why we have not yet detected such a field in laboratory experiments on Earth. It is suppressed in our dense environment. But in the vast, near-perfect vacuum of intergalactic space, or in the extraordinarily dilute early universe, the chameleon becomes light and long-ranged. Its influence can stretch across cosmic distances, potentially rivaling gravity itself. In the sparse environment of the universe's first moments, this field would have been free and active. It could have been the very driver of cosmic inflation or a powerful companion to the inflation, dramatically altering the dynamics of the universe's explosive birth. As it evolved and interacted, its changing mass would have modulated how it transferred energy into the primordial plasma during reheating. This turbulent, environment-dependent behavior would have directly imprinted itself on the gravitational waves generated in that epoch. The spectrum of those ancient ripples could carry bumps, wiggles, or a specific tilt that reflects the chameleon's unique mass-shifting nature, but the story does not end there. The chameleon's most profound signature might be written not in the wave's birth but in their journey. For over 13 billion years, these primordial gravitational waves have been traveling across the cosmos. As they pass through regions of different density through galaxy clusters, the halos of dark matter, and the vast cosmic voids, they would interact with the chameleon field present in those environments. Since the field's properties change from place to place, it would act as a variable filter for the passing waves. A gravitational wave traveling through a dense galaxy cluster might have its polarization slightly rotated or its amplitude minutely altered compared to a wave that traveled through an empty void. This would create a specific correlated pattern across the sky. The observed spectrum and polarization of the primordial gravitational wave background would not be perfectly uniform. Instead, it would show subtle anisotropies, faint variations that align with the large-scale structure of the universe. Finding such a correlation would be a smoking gun. It would mean the first tremors of space-time carry not just a memory of their creation, but a detailed travel log of their 13-billion-year voyage, marked at every turn by a ghostly field that hides in plain sight. Cosmic strings are not the only scars the early universe could have left behind. They belong to a broader, stranger family of relics known as topological defects, and their extended family includes entities even more bizarre: domain walls and magnetic monopoles. Where a cosmic string is a one-dimensional crack in reality, a domain wall is a two-dimensional sheet, a vast membrane of concentrated energy slicing through the cosmos. A magnetic monopole, meanwhile, is a zero-dimensional point, a solitary particle that carries a net magnetic charge, a north pole without a south, something never observed in nature. These defects are not random accidents. They are the inevitable fossils of cosmic phase transitions, formed when the universe cooled and its fundamental symmetries broke in specific, imperfect ways. The type of defect that freezes into the fabric of reality depends entirely on the mathematical pattern of that symmetry breaking. It is a direct map from the abstract laws of particle physics to tangible, macroscopic structures in space-time. Imagine a vast crowd all ordered to face north, but the command is given imperfectly. In some regions, everyone turns correctly, creating smooth domains of alignment. But where these orderly domains meet, you get lines of conflict, cosmic strings. If the symmetry breaking is different, you might get entire walls of misalignment or isolated points where the order completely breaks down, creating monopoles. This is the cosmic defect network, a web of frozen imperfections woven into the expanding universe. Unlike a single event like inflation, a network of these defects is not a one-time source of gravitational waves. It is an engine that runs for eons. From the moment they form in the early universe, these defects are dynamic and full of energy. Cosmic strings whip and snap. Domain walls under immense tension oscillate and collide. Monopoles and antimonopoles find each other and annihilate in bursts of energy. Every kink, every collision, every oscillation shakes the fabric of space-time. Each event sends out its own burst of gravitational radiation, but because a network contains countless defects spread across the entire cosmos, and because their interactions continue throughout cosmic history, the individual chirps and bursts from millions of events overlap and blend together. They do not create a single, clean note. Instead, they produce a rich, stochastic background, a cosmic static across an incredibly wide range of frequencies. It is the sound of the universe's frozen floors ringing out across time. The shape of this gravitational static is a direct fingerprint. The spectrum it creates, its loudness at low frequencies versus high frequencies, holds the key to identifying which defects, if any, filled the early cosmos. A network of cosmic strings produces a nearly flat spectrum across a broad band, a steady hiss. Domain walls, being two-dimensional, generate a spectrum that rises sharply with frequency, a louder roar at higher pitches. The presence of monopoles would add its own distinct texture to the mix. More importantly, the specific amplitude and slope of this background noise encode the energy scale of the phase transition that created the defects. It tells us the temperature of the universe when that particular symmetry broke, a temperature far beyond any earthly experiment's reach. By carefully listening to the gravitational wave background across different frequencies with instruments like pulsar-timing arrays, space-based observatories, and even future measurements of the cosmic microwave background, we are not just listening for a signal. We are conducting a cosmic archaeological dig. We are trying to hear the specific ringing of these ghostly structures to determine if our universe's vacuum is crisscrossed by invisible walls, threaded by indestructible strings, or dotted with lonely magnetic poles. A detection would be more than a new astrophysical source. It would be a direct readout of the symmetry-breaking pattern that defined the fundamental forces in the universe's first terrifying moments. The faint hum in our detectors could be the eternal vibration of a crack in reality's perfect order. The violent end of inflation was not a quiet fade to black. It was a cosmic crescendo, a period of unimaginable turbulence known as reheating. After driving the universe's exponential expansion, the inflatoned field had to decay. It could not simply vanish. Its immense energy had to be transferred, transforming into the hot, dense soup of quarks, gluons, and photons that would become our universe. This was not a gentle, orderly process. It was a chaotic, explosive event, a non-linear storm that would have shaken the very foundations of reality. The mechanism is thought to be parametric resonance, a process of runaway amplification. As the inflatoned field began to oscillate at the end of inflation, it did not decay particle by particle. Instead, it acted like a giant cosmic pump, rhythmically transferring energy into other quantum fields to which it was coupled. Think of a child on a swing being pushed at just the right moment. Each push adds energy, and the swing goes higher and higher, faster and faster. In the early universe, this resonance caused explosive, exponential particle production. Certain modes of these coupled fields were amplified so violently that the process became turbulent, a churning, boiling sea of energy where classical physics took over from quantum rules. Within this maelstrom, even stranger structures could have formed, oscillons. These are not particles, but long-lived, localized lumps of the inflatoned field itself, dense concentrations of energy that oscillated in place for thousands or even millions of cycles before finally dissipating. The cosmos would have been filled with these seething, temporary islands of energy, colliding and interacting in an incredibly complex dance. All of this violence, the resonant amplification, the turbulent churn, the birth and death of oscillons, made the reheating era a prolific factory for gravitational waves. Every collision, every sharp gradient in the energy density, every violent oscillation shook the fabric of space-time. Unlike the smooth, low-frequency hum from the stretching of quantum fluctuations during inflation itself, the waves from reheating would be a cacophony of higher-frequency ripples. They would be the sound of the universe being violently reheated, the crackle and pop of the cosmic furnace being lit. This gives us a second, independent channel to probe the dawn of time. While the inflationary gravitational waves imprint a pattern on the cosmic microwave background, the reheating waves would form a distinct stochastic background at much higher frequencies. Their spectrum would be a detailed fossil of the turbulence. The specific frequencies where the signal is strongest would tell us the energy scale at which reheating occurred. The shape of the spectrum could reveal the presence and behavior of oscillons, or the strength of the inflatons coupling to other particles. In essence, by tuning our future detectors, like the laser-interferometer space antenna or even more advanced concepts, to the right high-frequency band, we could listen to the symphony of reheating. We would not just confirm that inflation ended, but we would hear how it ended. We could discern whether it was a smooth decay or a violent, resonant explosion, and we would gain direct insight into particle physics at energies 1 trillion times beyond the reach of any collider. The first moments after inflation were not a blank page, but a page filled with the most turbulent, energetic script imaginable, and its echoes might still be ringing through the cosmos today. The profound quiet we have encountered may not be a puzzle of physics, but a condition of our own existence. This leads us to a theory that bridges cosmology and philosophy, the anthropic selection argument. It begins with a simple yet staggering premise. If the inflationary multiverse is real, an endless froth of bubble universes, each with randomly different physical properties, then every possible outcome of inflation is realized somewhere. In an infinite array of universes, some bubbles would have produced a deafening roar of primordial gravitational waves, while others would have generated only the faintest whisper. The strength of these waves is not arbitrary. It is intimately tied to the amplitude of the density fluctuations that seeded galaxies. A universe with very strong gravitational waves is also a universe with violently large density contrast. In such a place, matter would have clumped too aggressively in the early cosmos. Instead of forming graceful galaxies and nurturing stars over billions of years, matter would have collapsed catastrophically into enormous black holes or monstrous, short-lived stellar furnaces. The cosmic landscape would be chaotic and hostile, offering no stable platforms for planets, let alone the long, quiet epochs necessary for life to evolve. Conversely, a universe with gravitational waves too quiet likely had density fluctuations that were too weak. In that scenario, matter might never have clumped together at all. The primordial gas would have remained a thin, featureless haze, forever unable to coalesce into the galaxies and stars that are the cradles of planetary systems. Life, as we understand it, would be impossible. We find ourselves then in a universe with a very specific Goldilocks amplitude. Our gravitational wave background is not too loud and not too quiet. It is just right, or more precisely, just right for us. The fact that our most sensitive experiments find the signal hovering just at the edge of detectability is not a coincidence. It may be a direct consequence of anthropic selection. In the vast multiversal lottery, we could only ever arise in a bubble where the primordial tremors were within a narrow window that allows for complex cosmic structure. If the signal were much stronger, our universe would have been stillborn, collapsing into chaos before life could begin. We are not here despite the quiet, but because of it. This idea reframes the entire search. The non-detections from telescopes at the South Pole are not failures. They are potentially the expected signature of a universe fine-tuned for observers. Our continued push for greater sensitivity is a push to map the very boundary of habitability, to find the precise threshold where a universe becomes capable of asking questions about its own birth. The silence we hear may be the sound of our own cosmic address, the specific conditions that had to be met for us to one day listen at all. This final possibility is the most humbling of all. After 30 extraordinary theories, each offering a different cosmic genesis, we must confront the stark reality that the universe might simply be silent. This is the null hypothesis, a scientific term for the default position, the assumption that there is no signal to be found. In our search for the first ripples, it means accepting that primordial gravitational waves may be so faint they are forever beyond our reach, or that they do not exist at all in any detectable form. This is not a failure of imagination, but a profound scientific statement in itself. Many compelling models naturally predict a whisper, not a shout. Low-scale inflation, for instance, is a perfectly viable version of the theory where the energy of the inflationary field is exceptionally small. The quantum tremors it amplifies are correspondingly tiny, generating gravitational waves with an amplitude so minuscule they vanish into the cosmic noise. Another elegant idea, the Curvaton scenario, offers a different path to silence. In this model, the density fluctuations that seeded all galaxies did not come from the inflaton field, but from a secondary field called the Curvaton that decayed much later. The inflaton's job was solely to stretch the universe smooth, a task that produces almost no gravitational waves. The Curvaton then provided the seeds for structure, decoupling the creation of matter from the production of space-time ripples. The result is a universe that looks exactly like ours, rich with galaxies and clusters, but born in near-total gravitational quiet. A definitive, persistent null result from our most advanced observatories would therefore be a revolutionary discovery. It would not be an empty silence but an informative one. It would systematically rule out vast swaths of the inflationary landscape, sweeping away the loud, high-energy models that have dominated our theorizing for decades. It would force cosmologists to abandon comfortable assumptions and gravitate toward these quieter, more subtle origins. We would have to fundamentally reconsider what the universe's first moment can tell us. If the primordial gravitational wave background is truly undetectable, then the story of creation is locked away in other, more elusive fossils. Our focus would shift entirely to the intricate details of the cosmic microwave background's temperature and polarization maps, to the subtle clustering of galaxies, and to the faintest whispers from other eras. The silence would be a guide, narrowing the infinite possibilities down to a select few where the birth of everything was a gentle, almost imperceptible event. In the end, the greatest discovery might not be a signal, but the resonant, shaping power of silence, teaching us that sometimes the universe's deepest secrets are kept not in what it says, but in what it chooses not to say at all. This grand exploration across 30 frontiers of thought reveals a universe far stranger and more creative than we ever dared to dream. We have journeyed from the quantum tremors of inflation to the silent geometry of a no-boundary beginning, from colliding brains to a cosmos woven from vibrating strings. Each theory, whether anchored in established physics or soaring into speculative realms, presents a unique signature waiting to be found in the faintest hum of space-time. The true power of this quest now comes into sharp focus. We are not merely hunting for one specific signal. We are using the universe's first whispers as the ultimate experimental probe. These primordial ripples are messengers from an epoch of unimaginable energy, carrying encoded within them answers to our deepest questions. Their detection or their profound silence will directly test the reality of quantum gravity, the existence of extra dimensions, the validity of the multiverse, and the very laws that wrote reality into being. This is why the next few years hold such breathtaking promise. A new generation of eyes is turning to the cosmos. On the icy plains of the South Pole, telescopes are scanning the ancient light with unprecedented sensitivity. In the quiet of space, missions are being designed to listen for the mid-frequency chorus of cosmic collisions. Across our galaxy, astronomers are using pulsars as a galaxy-sized gravitational wave detector. Any day, any moment, one of these experiments could capture a flicker of data that doesn't fit the old story. That single anomaly, that faint pattern in the noise, could be the key that unlocks one of these 30 doors, forcing us to rewrite every textbook on how everything began. The universe has held its first secret for 13.8 billion years. We are now, for the first time, truly listening. Which of these visions of creation resonates most deeply with you? Do you find elegance in the cyclical bounce, or does the holographic principle bend your mind in the most compelling way? Share your thoughts below and subscribe to journey with us into the next great cosmic mystery.